Hello, so in this video we're going to talk a little bit about antiderivatives. Now, the easiest way to kind of understand antiderivatives is to look at, say for example, the derivative of f of x. Now, granted that the limit does exist, we'll find that that's going to be f prime of x. Now, note that basically that you have that f of x is possibly, we'll just say, is equal to y. Now, what that means is that when you take the derivative of y equals f of x, it's like you get this relationship of the differential dy divided by dx is equal to f prime of x. Now, most likely you learned that whenever you have this notation, that essentially this tells you that you have dy over dx equals to f of x, f prime of x. So if we multiply by, let's say, dx on both sides, and this is not technically the correct, in this sense, it's not really correct by saying multiply by dx on both sides, but at least it's more or less giving you an idea that what we're about to say is that the differential dy is equal to f prime of x multiplied by dx. Now, whenever we want to go and reconstruct the original function, normally we just tend to say that, well, all that we need to do is just take what we call the antiderivative on both sides by using what is called the integral symbol. So what this does is it reconstructs the original graph as follows, as y equals 2. Well, the antiderivative of f prime of x would be just f of x. So we would have f of x. But however, this would be plus the constant that we'll call c. So in reconstructing the graph, we have to account for that maybe that there was a constant of which that, when you take the derivative of that, that's going to be 0. Now, in the most traditional sense of, like, say, for example, the textbook, usually we tend to say that we let f prime of x to equal the derivative of f of x, or big F of x. Now, if we do that, then of course that means that the antiderivative, so f of x, would have to be equal to f of x plus c. So this is the most important piece, is like, how exactly did we find this function? Well, the way of which that we found this function was through that process of saying that, well, f of x is equal to the integral of f of x plus, not plus, but times dx. So in this case, we have the determination of, like, how are we finding big F of x? Let me see. This should be right because, yeah, okay, this is correct. Okay, so let's say that we were to consider the following, where we just want to find the antiderivative of, let's say, for example, that we say that we have y prime equals to, let's say, 3x squared. And we can just leave it at that, for example. So whenever we do this, we have to think, okay, well, I know that the way of which that I got this was by using n, okay, not n equals, but using that n multiplied by x to the n minus 1 is how we found the derivative. Okay, but if we're trying to reconstruct it, it's almost as if we need to add 1 to here and then divide by the same thing in order to cancel out the n. So with that, we're just going to say, okay, well, if we're trying to find the antiderivative, that would be 3x to the 2 power, but since we subtracted 1, we're going to add back. But how do I get rid of the 3? I just need to divide by 3. But then I also need to put plus c, and that equals to y. But when we simplify this, we end up with x cubed plus c. So we found the most general equation that gave us that the derivative was 3x squared is x cubed plus c. Now, there is a way to kind of consider like, okay, why is it plus c and what does that mean? It means that you would be looking at the family of graphs that are cubic but shifted up 1 unit, 2 units, 3 units, and similarly by minus 1, minus 2, and so on. So for example, this is going to be our function x cubed. But another possibility, for example, is, let's see, we can write it like this. Another example is like, yeah, we can say x cubed plus 1. So we have x cubed plus 1, but then this one is x cubed. But I can write, for example, another one, like another graph, where I'll say that, okay, well, another possibility is that we have that it looks something like this. And that's a little tight in between, but hopefully you get the idea that, this one is going to be x cubed minus 1. So these are what we call the family of curves. And that's because we don't know, like, whether it's plus 1 or whether it's 0 or whether it's minus 1. Now, there's a way to put all of this together in the sense that, we can use like a formula. So, for example, if we have that we're integrating or taking the antiderivative of x to the n dx, well, that's equal to, okay, so here's what we end up with. We end up with the antiderivative of x to the n is x to the n plus 1 divided by n plus 1, and that'll be plus c. But this is provided that n is not equal to negative 1. So it could be anything else, but just not equal to negative 1. So we kind of have our first set of formulas. So this is kind of like what we call the anti-power rule, because we're adding back the original power in this case. Now, when we do these, all that we need to do is just add 1 and divide by the same thing, in order to cancel out the constant in front. So let's see. Let's do an example. Okay, so we can do an example where we have, let's say that we want to find the antiderivative of, let's say, 2, and then we have the square root of x dx. Now, if we want to do this, then all that we need to do is say, well, this is the same as 2 multiplied by x to the 1/2. Okay, so this is dx, but when we solve this, this is going to be 2 multiplied by x to the 3/2, because you have 1/2 plus 1 is 3/2, and then you're dividing by 3/2. and then this is plus c. But if we go ahead and we bring this together, basically you have that you end up with 2 multiplied by 3 halves, not 3 halves, 2/3. Yeah, I've got to be careful with that. Okay, so we have that that's going to be 2 over 3 multiplied by x to the 3 halves plus c. Now what this means is that we found that the solution is 4/3 x to the 3 halves, but you need to make sure that you add the constant c. Now, one thing that I am being a little careless with is this 2 right here. So notice that basically it's like I said, ignore the 2 and then just work on figuring out what the antiderivative of the square root of x is. So in this case, it's kind of like I took that for granted by not looking at the, or kind of like ignoring that 2, because we technically haven't established rules on how do you get the antiderivative of a constant. But if we do like kind of like another one, for example, like if we look at another example where we have, say for example, we want to integrate or take the antiderivative of, okay, so let's say that we have negative 1 over x squared, and then this is dx. Well, accordingly, we would actually say that this is going to be the antiderivative of negative 1 times x to the negative 2. Now, in a way, this is still the same thing where, we're kind of being a little careless with the constant. So, right, how about this? Um, hmm. Okay, so how about this? We'll go ahead and continue this one, and we'll just say that this is going to equal to, okay, so this is going to equal to negative 1 times x to the negative 2 plus 1, all divided by negative 2 plus 1, and then that's plus c. So this gives us minus x to the negative 1 divided by negative 1 plus c. But as you can notice, that this is going to be where you end up with negative 1 over negative x, not x squared, but x to the 1. And I mean, if you can already notice that you're going to cancel out the negatives, okay, so that should just be 1 plus c. So this is going to be 1 over x plus c. So that's the antiderivative of negative 1 over x squared. Now, this gives you certain properties essentially that we can establish that normally, we would establish maybe from the very beginning. So, for example, we have that the properties state that basically that you have that the integral of a constant times f of x, so constant times f of x dx is equal to the constant times the integral of f of x dx. Now that allows you to kind of ignore the constant like we did in the previous 2 examples. So another is, for example, that you have that the integral of f of x dx plus or minus the integral of g of x is equal to the integral of both the f of x and then plus or minus g of x. So more or less, like, it's just telling you that you can either integrate it term by term or each function individually, or that you can just add or subtract first and then take the integral. So it's more or less like the same thing, but it helps you with respect to properties or polynomials. So for example, like if we have the following integral, so let's say that we have an antiderivative of 6x squared plus 8x minus 9. Now, according to this, we can actually just say, well, we know that basically we're just going to add an x's power, and then just divide by the same thing. So that's going to be 6x cubed divided by 3 plus 8x squared divided by 2 minus 9x, because basically you have that's kind of like x to the 0 plus 1 divided by 1, which is still just x. And then we have plus c. Now cleaning this up, we have 2x cubed plus 4x squared minus 9x plus c. And then that would be it. So as long as we kind of have down the thing about that you can find the antiderivative of any polynomial, then yeah, you should get more or less the same thing. And notice that if we were going to check our work, we would just need to differentiate the antiderivative. So like you have that the derivative of 2x cubed plus 4x squared minus 9x plus c is just going to be 6x squared plus 8x minus 9 and then plus 0. But the 0 is going to be gone, so in that case that just goes away. But that's a nice little way to check your work, if anything. Okay, so let's say that we have kind of like another example of solving an integral, and we call these indefinite integrals. So if, for example, that we have, let's say, okay, so we have example, and let's see, well, let's suppose that we have x plus 1, and all of this is divided by the square root of x, and we have the integral of that. Okay, now this is going to be kind of up to you on how do you want to do this, but the easiest way that we can do this problem is just to rewrite it. So like we have the integral of x divided by the square root of x plus 1 divided by the square root of x. Now what this does for us is that it reduces even further. It reduces as the square root of x plus 1 over the square root of x, and then we just say, okay, that's just going to be dx. But if we go ahead and we furthermore say, like for example, that we have the integral of x to the 1/2. Okay, so we have x to the 1/2. There's something happening with my tablet. And then we have plus x to the negative 1/2. And we'll just do this. Okay, so, and that's going to be dx. So this is going to give me x to the 3/2 divided by 3/2 plus, okay, so this is going to be, let's see, that's going to be x to the 1/2, and then all of this is divided by 1/2, and this is plus c. So what this means is that we have 2/3, and then we have x to the 3/2, and then we have plus 2 square root of x, and this is going to be plus c. Now you can get a little bit clever where you just say, well, isn't that really just, for example, like 2/3 multiplied by x and then the square root of x, and then you have plus 2 and the square root of x. There's something really going on with this tablet. So we have 2 root x. Okay, hold on. can just do this because it'll be easier. Oops. And then we have to do plus c. Okay, so this should work for us. Okay, so the next thing of which that we can look at, for example, is more properties, because we have that, for example, we have that if we have some more integrals, such as the exponential or logarithmic, we have that there are specific ways that we can find those. So like for example, we have that the antiderivative of e to the x is just e to the x, and then it's plus c. The other thing of which that we do have is that, okay, so we'll say like this, for some positive a, where a is not equal to 1, we have that the integral of a to the x, and then we'll just say dx, is equal to a to the x all divided by natural log of a, and all of this is plus c. Okay, so that tells us that we have that that's going to be yeah, a to the x divided by ln of a plus c. Now you do have that there is a part where you would have that their constant, that there might be a constant left over, and that's okay. Now the other thing of which that we do have is, okay, just one more. We have that the integral of the, let's see, x to the negative 1 dx, this is equal to natural log the absolute value of x plus c. Now we won't really talk too much about like, okay, how do we find the antiderivative of a natural log, because usually it's just itself. So like right now I can't really do too many logarithms without introducing like a constant within the absolute value signs, if that makes sense, because it requires a bit of u substitution. Now, and that goes for the same for e to the x. So, you know, you just kind of have to practice. Like, for example, if you have the integral of e to the x, and then you just push like a, maybe like a constant in the front, then you know that that's going to be equal to 2 e to the x and then plus c. Okay, so let's actually look at some applications. So for example, we know that a application, one possibility is, for example, if you look at the position function, so like s sub t equals to negative 1/2 g multiplied by t squared plus v sub 0 and then t and then plus s sub 0. If you have something like this, then in that case you can say, like, you know, for example, that the derivative of the velocity, I'm sorry, the derivative of the s position, or the s of t, is equal to s prime of t. And then we have that if we look at the acceleration, or the second derivative, this is equal to s double of t, which basically means that if we know what the velocity is, then we know what the position function is. But we would need to know, like, of course, like what is the initial velocity. So let's say that we are going to use our example of the, let me just check to see, active. Okay, I'll have to fix that later. Okay, so let's say that we have this, where we have the integral is going to be where we take our velocity function. So like, for example, uh, negative 32t, and then we have plus 96, and then let's say that, okay, so let me just erase this. This is so bad. The pen appears to be giving up on me. Okay, so let's say that we have our integral, and this integral is basically equal to the s of t, but remember that it's going to be plus some constant. So to kind of cap this off, like we're just going to say that, let's say for example, that the initial, uh, let's see, 6, 7, maybe 8. Okay, so let's say that we just say that this object that was thrown upward was when it was from the ground up. So if that's the case, then that means that when we go ahead and we find the antiderivative, it's going to be that s of t is equal to, well, we have that if we use the anti-power rule, that's going to be negative 16t squared plus 96. Okay, something's really going on. Okay, so 96, 96t, and then we have that. That's it, because if you look at the constant, that's going to be in addition to this. The way that I kind of view it is that, well, if we have that it was from the ground up, then basically that means that this value right here, um, this value right here is equal to 0. So what that does is it tells you that the initial the position function is just going to be let me just not even write it. The initial function is just, or the position function, it's just going to be s of t equals to negative 16t squared plus 96t. Okay, so this will tell you that if you kind of just work out where you look at the antiderivatives, that using the different rules, that it'll allow you, like, to reconstruct the function. And sometimes you do have to rewrite it, like so that you're able to take the integral of it. Okay, so the next question, or not question, but the next set of topic will be 15.2, which deals with the not antiderivatives necessarily, but using a technique called the substitution method.